Hey kiddos, and welcome to our last podcast for physics. We're looking at 3.3 efficiency. And when we're talking about efficiency in terms of physics, we're talking about input and output energy. We're definitely not talking about this example of efficiency. Being efficient is awesome, but we want to be able to calculate the percent efficiency of something. All right, kiddos, let's get started. Okay, so first of all, we use machines to convert energy added to it. We call that energy input energy. To do a different form of energy, useful energy output, that we may want to do work, which is your useful work output. Okay, a system will always lose some energy as wasted heat, as we knew from our previous podcast. In other words, the energy input is never equal to the useful energy output. Very rarely, or if ever, actually, do we get 100% efficiency. And a perfect machine, which is 100% efficient, is converting energy is only theoretical. It would be nice if that could happen where you have a machine that is 100% efficient. That's never going to happen because we live on Earth and we have gravity and friction, all those good things. So efficiency is a measurement of how effectively a machine converts input energy into useful output energy. And we have a cool little formula. It's our last formula. Efficiency is equal to total work output over total work input. This gives us the efficiency as a decimal between 0 and 1. Sometimes, or most often, we look at efficiency in terms of a percentage. Like, what is the percent efficiency? If that's the case, we're looking at total work output over total work input times 100%. Okay, you have to multiply by 100% because that's going to give us the percentage of the efficiency. Okay, let's take a look at our first example. In lifting a car, the total mechanical energy input, so we have the input, hoist, is 5.61 times 10 to the power 4 joules, while the useful mechanical energy output is 1.96 times 10 to the power 4 joules. Calculate the percent efficiency. So we're looking at for percent efficiency. That's what we're looking for, right, kiddos? We have our input, which is equal to 5.61 times 10 to the power 4 joules. And we have our output energy is equal to 1.96 times 10 to the power 4 joules. Okay, so let's use our formula. Percent efficiency is equal to total work output, over total work input, don't forget, times 100, right? So we have percent efficiency is equal to 1.96 times 10 to the power 4 joules over 5.61 times 10 to the power 4 joules. We multiply all that by 100. And we get an answer of 34.9% when we use our calculator. Okay, next question. A small electric motor has an efficiency of 85%. Now we have this given to us, 85%. In lifting a small boat, it produces 15 joules of mechanical input energy, and calculate the useful mechanical output. So we're looking for our output energy. Now in this case, we're talking about mechanical energy, so it's important, you can just use output energy, input energy. We're looking for the output energy. We have our input, and our input energy is equal to 15 joules, and we also have our percent efficiency, which is equal to 85%. Now, really importantly, kiddos, we know that, I'm just going to spend 2 seconds on this. We know that 85% is 85 over 100, right? We can't use 85% in our mathematical equation because that's a very different, percent is a different concept than the actual raw number. The raw number is 0.85, and this is the number we use in our actual work. So we know that if we rearrange our formula, right? We have percent efficiency is equal out to output over input. And we are looking for, I'm just doing this really slowly, x over input, because we are looking for x, right? So x is equal to, because remember I have to multiply this by input to get rid of it. So x is equal to input energy times percent efficiency. Okay, but we're not going to actually use our percent, we're going to use the decimal. So we have 15 joules times 0.85, which is equal to 13 joules. Okay, very important, guys, that you use this in your math. If you use the 85%, okay, if you use the 85%, if you go 15 joules times 85, oops, I'm trying to say 85, 15 joules times 85%, then you have to divide by 100. So this is your option A of how to do it, and this is your option B of how to do it. Either way, you're going to get the same answer with just 13 joules. Okay, last example. A Bunsen burner supplies 4.0 times 10 to the power of 3 joules of heat. So that is what the machine is supplying. Only 125 joules of heat is gained by the beaker. Calculate the percent efficiency of the burner, and we're looking for the percent efficiency, okay? So let's take a look at everything that we have. We have our input energy, which is supplied by the machine, is 4.00 times 10 to the power of 3 joules. We have our output energy. So even though the machine is supplying 4.00 times 10 to the power of 3 joules, how much was actually like gained or lost? And it's 125 joules in this case. That was the only amount of heat that is gained by the beaker. So it was only able to use 125 joules out of the input of 4.00 times 10 to the power of 3 joules, which is equal to 4,000 joules, right, kiddos? So percent efficiency is equal to output energy divided by input energy times 100. Okay, so my percent efficiency, it's an E, is equal to 125 joules over 4.00 times 10 to the power of 3 joules. And I'm going to multiply that by 100, which is only going to give me 3.13% efficient. So that's a poorly efficient machine, but a lot of machines are inefficient actually, because so much is used up as heat or wasted as heat. That's it. That's all. We have finished. Physics is over. I hope you guys enjoyed it. I definitely enjoyed it, and have a great day.